Hello guys, welcome to my presentation. Today I'm going to talk about limits. I'm going to go over basic limit concepts and we're going to do some questions at the end. Okay? So what is a limit? A limit is what we call it, for now we'll call it an intuitive definition, is the value that a function approaches as the x variable approaches a certain value. So as the x goes to a value, the function will approach a value. And we write it like this. I'm sure you guys have seen it in differentiation from first principles as h tends to 0, the distance, and then we get a letter gradient basically. So yeah, as long as we can make x really close to a, then we can get f of x really close to L value, the limit. We're going to do an example. I'm just going to point out, so this limit is that limit of x squared as x approaches 2 is 4, which makes sense since if you put 2 into this function you get 4. And for this to be true, we've got to take x from less than 2, and we see that as it gets closer to 2, the function will approach 4, and from the right side as well. So let's say we have x equals 3, then we have 9, and it'll go down to 4 as well. So for the limit to exist, we need both of these from both sides to approach the same value. And that's basically, I'll go into why limits matter. Because they're in calculus, we use it in integration, differentiation, everything. Also, to avoid expressions like dividing by 0, when we have a gradient differentiation, right? We can't take h to be 0, but we take h as it goes towards 0. So it gets closer and closer, and our value for the gradient gets closer and closer to the true value. Also, when we have discontinuities in graphs, we can see how the function behaves around that point, and what it will do basically. This is what I was talking about, one side of limits. So for the full limit expression to be true, you need the left side limit. So this is left side, so minus since for the left. And then right side from the right, they need to exist and be equal to each other for the full limit to exist. So you know this sign is necessary and sufficient for, so if and only if this, if this doesn't exist, let's say the right side limit didn't exist, then we had the full limit does not exist. We can still say this one existed if it did, and it's of a value, but the full limit doesn't exist. Okay. So here is a function with a discontinuity in it. We see that when x is not equal to 1, we can just cancel this, and we get y equals x plus 1. So this is the graph of y equals x plus 1 with a discontinuity at x equals 1. But it's undefined, because we'd be dividing by 0. Well, it would be indeterminate actually, since it's 0 over 0. And so we want to see what value the function approaches as x approaches this discontinuity, where we can't actually get to it, but we want to see what happens when we get close to it. So we can do this by plotting a table of values. This is like a traditional method. And we see, as long as x is not equal to 1, we can just take this as y equals x plus 1. We see as x gets closer and closer to 1, f of x will get closer and closer to 2. Same happens with the right side. As x gets closer and closer to 1 from the right side, the f of x will get closer and closer to 2. And so we can see intuitively, just from this method of seeing how the function approaches its value, as x approaches its value, numerically, we see that the limit is 2. Okay? Yes. Makes sense. Okay. Now, we're going to go on some limit properties, so we can actually do some limits. So the first one is that we can factor constants out of limits. Like the limit of 2x is equal to 2 times the limit of x, for example. These are as long as the limits for these functions exist, and c is just a constant. Next one is that we can add limits or minus them, since if they both exist, they're just numbers, and we just minus them from each other. The minus limit, or the added limit, is equal to the total limit of the functions added together. Next one is we can multiply them as well. So we can take out the limit, kind of. Next one is we can divide them, as long as g of x is not 0, or the limit of gx is not 0. and we can take out exponents, and finally the constant will stay a constant no matter, or the limit of the constant as x approaches the value will be the constant because it doesn't change. And for x, the limit of x as x approaches a is a. We can see this if we have a line y equals x, as x goes to a, then the y value will approach a as well. Yeah. We're going to do this example now. So just using limit properties, we should be able to solve this. So to start off, what do you think we should do? Yeah.
Probably plug in -2.
I don't think we can do that. No, we can do that, but we can't do it immediately. Yeah.
Just like separate the terms first.
Separate them, right? Yeah. So we have to write the word limit a lot in these ones. So we've used the limit property of addition and subtraction. Oh, that's a terrible one. Yeah. So what can we do next? We have the sorry.
We can factorize out to a constant scale.
Yeah. So we get 3. Is there anything else we can do? Because I kind of don't want to write this one again. Can we do anything with the exponent now? Yeah.
You can bring the power of 2 outside.
Yeah. Like this. Take the 5 out. And we can just take this to be 9, right? Because it's a constant, -9. Now we can use the last rule and plug in x equals 2, because the last way rule. So we get 3 minus 2 squared times 2 is 4. And then plus 5 times -2 is -10. -9. And we get -7. So the limit of this function as x approaches 2 is -7. Cool. Now we're going to use a fact which will help us solve limits a lot quicker because it normally takes ages by just writing out limits so many times. And the fact is that if we have a polynomial, or a nice function p of x, we say that the limit of p of x as x approaches a is just the value if we evaluate at a. Now this is because they're nice functions, or continuous, as some of you guys know. And so this includes polynomials, exponentials, logs, trig functions, yeah, all of these which are nice. I'll get onto that in the next slides. So for this one, using the polynomial fact, we can just solve this directly by plugging in. So we would get z. We just plug it in, so we get 6 minus plus 10 minus 2. And we get minus 3, 7. Yeah, we get 7 over 6. That was so much quicker because of this fact. So, that's wrong. Say again?
I think that's right.
Okay, cool. Now we've got infinite limits. So infinite limits aren't when x approaches infinity. Sorry, x approaches the number infinity. We use infinity as a concept here. It's when you describe it getting really big or really small. And we've got the graph of 1 over x, which is a very good example because it is a vertical asymptote here and a horizontal asymptote here. So for an infinite limit, we say that the limit of f of x as x approaches a is infinity. And this means that as x approaches some value, let's say x approaches 0 from the left, it's going to be negative infinity, right? It's going to get lower and lower. And as x approaches from the right to 0, it's going to go to infinity. So, yeah. This is from the right, so this is infinity. This is negative infinity. So what is this?
It does not exist.
Correct. It does not exist. I'm not going to write that. It takes ages. But yeah, that's just the idea of it getting really big as we approach a value of x. And for the same thing, we have limits at infinity, which is the horizontal asymptote version. So as x approaches infinity, the function will approach a value. So what value does the function approach as x approaches infinity?
0.
0, yeah. And as some say minus 0, okay. As the x approaches minus infinity, again the function also approaches 0. So yeah. Okay, we're on to continuity now. So I said a function, this is a nice function. So what I really mean is continuous. By continuous, I mean you can draw a line over it. Like say you've got a quadratic, right? You can trace the line of quadratic without letting your pencil up. So there's always going to be a value at every value. There's going to be infinite many values, and there's going to be infinitely many f of x values, y values, yeah. And so we've got this, and we can see that, actually, who can tell me where this is continuous from? For just, yeah. Like just one point, like one area.
Then we get an infinity up to minus.
Infinity up to here?
Yeah.
Yeah. Okay, cool. What's another section? Anyone? Yeah.
-2 to 3.
You sure? There's a hole in here, so. Oh, including -2 or not?
No,
And not including 3, right?
including that.
So we can trace a pencil from here. You can stop drawing. Okay. We can trace it from here, and we can't trace it here anymore because there's a hole. We've got junk, and then we can trace from here onwards. So it's continuous from here to here and onwards. Now, what I really wanted to get onto was the epsilon delta definition. This is really long. I'm just going to say it. So the definition, the limit of f of x as x approaches some constant c equals L is defined by, for some epsilon in the reals greater than 0, there exists a delta in the reals greater than 0 for all x in the domain of f such that the distance from x to c is less than delta. It implies that the distance from f of x to L is less than epsilon. So what that really means, I just want to say it because it's cool. For all epsilon greater than 0, we can find, epsilon is just an arbitrary number we can pick. It's like an error boundary. Then we can find another error boundary delta such that the distance from our function f of x to our limit L is less than epsilon whenever the distance from x to a is less than delta. Yeah, so before we said when x gets close to a, f of x will get close to L. Here we're quantifying it using some values we can find. We can say when x gets within delta range of a, then f of x will get within epsilon range of L. So when it gets close here, this will get close here as well. It must get close there. So yeah, that's what the limit actually means. Yeah. Well, this is modulus, so it's distance. Same here. Now we're going to do some examples. Did I? Yeah, okay. They might seem pretty futile because you're thinking, of course, x squared is going to be 0 at 0, but still we need to prove things properly. So we're going to start by giving ourselves an epsilon greater than 0, and we're going to choose a delta well, I'm just going to, it's obviously going to be greater than 0, but we don't know what to choose it as yet. So now we're going to suppose, okay, let me write out the condition that we need to be true for this to be true. We need We need this to be true, basically. So whenever this is true whenever this is true. We can obviously simplify this down to just mod x and mod x squared. So we're going to start from this expression. We've got mod x squared is less than epsilon. So what we want to do, what we want to do is we want to get this x in the form of this x, so we can find a delta that matches, that corresponds. So they already look quite similar, and one thing we can do first is to take out the square from the absolute value bars. And now, the next step is to square root everything, so you just have mod x is less than square root of epsilon. And now it looks like if we choose delta to be root epsilon, then this thing will hold, because it will be within root epsilon range, and this will be epsilon range. So we can choose delta equals root epsilon, and we know epsilon is greater than 0, so delta will be greater than 0. And we can check it, we can just plug it back in. We can just say, this is kind of just a check step. Less than delta squared. Does everyone know why I did this? Because of this inequality, which we found that delta equals. We just choose delta equal to this. So this is less than. Oh, well, actually, both corrected. And now we're proving it. Yay! How much time do? Okay, I can do one more. We're now gonna do. Should be there. Let's take the limit. So let's prove this now. Well, we've got given epsilon greater than 0. So then we choose delta equal, we don't know what it's equal to yet. And then we've got the statement. We're going to assume this is true. And then we're going to check it with this final bit. We want to get this into that form again. So what we're going to do, we can simplify it. 5x minus 10. And then we can simplify that to 5x minus 2. Less than epsilon. And so, what do you think we should choose delta as?
Epsilon over 5.
Yeah, correct. That's it. It's fairly easy, but wait, do you guys understand it conceptually? Like a range value, epsilon delta range, okay. Well, we still have time, okay. I can do an even harder one.
Are you running out of space?
Okay, so let's prove this with epsilon delta. We've got we're going to choose a delta, and we've got to suppose that x minus 4 less than delta. Now we're going to check finally with okay, so we should factorize this, right? X squared plus x plus 2. And then we've got, is that right?
Minus 20.
Sorry, minus. Now we have x plus 5 and x minus 4. So we've got some term which we don't want in here, which will prevent us from getting to this. So So what we're gonna do is now assume, we're gonna make the assumption that the distance from x to 4 is less than 1. We're making this assumption because we can make it really close to 4. If we want. And what this means is that taking out the modulus, right? Yep. And then we can convert this into x plus 5 by adding 9, right? So we've got 10 and 8. And now we have that the modulus of x plus 5 will be less than 10. So we want to choose the bigger value to find a bigger range. And not, if we choose a smaller value, it might not be right. So if x plus 5 is mod x plus 5 less than 10, we can go back here and we can say that, x plus 5, x minus 4 is less than 10 x minus 4, mod x minus 4, right? Which is less than epsilon. And so finally, we can choose our epsilon as, we can choose our delta as epsilon over 10. But we've also introduced a 1 here. So it's got to be the smaller of them. If this epsilon over 10 is smaller than 1, we'll choose it. But if it's greater than 1, we'll have to choose 1, right? So we're going to have to do something with the minimum function. And this will allow us to choose a smaller one of the two. Cool. Yeah.